All right. Good afternoon, ladies and gentlemen. So today we're going to be talking about fuzzy searching in prefix tries. You should at this point have already listened to the original prefix try section video, and you should have listened and try to follow to the try traversal video. That said, we are going to be reviewing some of this material. Okay, so the topic for today is fuzzy matching or fuzzy searching in the prefix try. The idea is, can we use the prefix try data structure in addition to fast retrieval of the queries that we're looking for? Can we also tolerate certain amount of errors in our searching, right? Now, the algorithm that we're going to be discussing for the prefix try searches is essentially a modification of a perfect match searching in a prefix try with an addition of the try traversal. So it will be important for us to recap both of those algorithms really quick. And then finally, after we finished discussing the algorithm, we're going to talk about space and time considerations and what does that imply. So what I've done here is I've put together some queries that we are going to be considering for this exercise. Remember, the problem that we've been trying to solve throughout this class is how do we take a large number of queries, all of a specific size, and how do we search these queries inside of our big subject sequence, right? So our queries in this particular case are going to be these 6 5-character long fragments, and our subject, the genome, is going to be this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-character long sequence, right? So just looking at these queries, you should probably notice that these queries are kind of perfect for a prefix try, right? There's a lot of repeated sequences, like these ACs are repeated almost everywhere. And then you have this ACT that's fairly common. And then you have this ACTG. So lots of prefixes to be reused, okay? So how does prefix try retrieval, fuzzy prefix try retrieval work? Well, first things first, let's go ahead and build our prefix try, right? So step 1, build the prefix try from the queries. So let's go ahead and quickly do that. So this is going to be our root, right? So let's start adding one sequence at a time to our prefix try. So let's see, A, C, T, and let's go with G and A. Perfect, right? So that's first string of characters added. Now let's go to the next one. A already exists from the root, so we don't have to create a new node. C already exists from the root, so we don't really have to create a new node. T exists, G exists. So the only thing that we really need to do to add this sequence to our prefix try is to add the T node, right? So let's go ahead and do that. Let's add the T. Perfect. Same thing here. A exists, C exists, T exists, G exists. Here they are. The only thing that we really need to do here is add a G node to make things a little bit symmetrical. Let's add the T node over here. So now we have this fragment. A, C, and T exist. A, C, and T. Now we need to add T and an A, right? So let's go ahead and do that. T and an A. Okay, perfect. This is added, ACTGC, ACTG exists. So the only thing that we really need to add is a C. Let's go ahead and add, let's make things symmetrical. Why don't we make this into an A and this into a C? Okay, perfect. So now this fragment or query is added, and now we need ACAAA. So right, so we're going to need to have A, and A. Not the prettiest prefix try in the world, but hopefully everybody agrees with me that all of our queries have been added to our prefix try. Great. So how does normal prefix try searching works? We are going to take our subject, which is right here. We're going to break up the subject into 5 mers, because that's the length of our queries. So we're going to look through the first 5 characters and the next 5 characters and so on and so forth, and search for these characters in our prefix try, right? So the idea is we are using the we are using the characters of the subject to try to trace a path through the prefix try. Okay, so let's try it. ACTGG. Does A exist from the root? Yes. Does C exist from the root? Yes. Does T exist? Yes. Does G exist? Yes. Does G exist? Yes. Perfect. We found the first 5 characters. These 5 characters are present in our prefix try, right? And we had to make 5 steps to do so. Then we look for the next 5 characters. This set of 5 characters begins with a C. There's no path through the from the root that goes to C. That means we're done, right? We've essentially realized that there is no possible match between CTGGA and whatever's in our prefix try as soon as we saw the first letter. Great. Same thing is going to happen when we try to consider TGGAG. Same thing is because there's no T hanging from the root. Same thing for this. Same thing for this. So yes, no, no, no. The next time we really are going to be considering the actual path is when we look at these 5 characters. A is going to exist from the root. That's great. However, there's no way to get to a G, right? There's no way to trace a path AG TGG, right? Because there's no G hanging off from this node over here. So great. So that means that the only set of 5 characters that are present from our subject that are present in the prefix try is the first 5 characters. Okay, great. So then let's put down the steps of the algorithm. So algorithm for the perfect match. Algorithm for perfect match search is going to be use the characters of the subject to chart a path through the prefix try, right? Use. Great. Now there's only really 2 choices. If the path exists, you move on to the next character and continue. If the path does not exist, you failed, right? So let's handle the easy case first. If no path. You fail. The set of characters does not exist in your prefix try. If path exists, meaning that you can move on to the next character in your subject and still continue to chart a path through the prefix try. So if path exists, you move on to the next character, right? On to next character in the subject. We need a stopping condition, right? So if you manage to reach a leaf node, you found the thing that you were looking for, right? So the query is found. Okay, so with this, we have our failure criteria. If you cannot move on to the next character and still chart a path through the prefix try, you fail. We have our success criteria. If you made it all the way to the last node of the prefix try, technical difficulties. If you manage to get all the way through to the leaf node, that means the thing you were looking for is found, and the meat of the algorithm really is here. If possible, move on to the next character. Great. So this is the perfect match searching in the prefix try. We've covered this before. Great. So now that we've recapped it, we're good to go. How do we traverse through all of the characters through all of the nodes in the prefix try? Let's go ahead and make a copy of this. Okay. So here is our prefix try. How do we do traversal? Well, in the traversal lecture, you have been introduced to one of the ways to do the traversal, and that is to use a secondary data structure to keep track of the paths that you have not yet followed, right? So the idea is you are here in the root. You can only really go down to this A node. So you go down to the A node. Here, you can only really go down to the C node. So that's it. Here, there's two possible paths that you can go to. So what you're going to do is you're going to say, hey, how about I have my special data structure that's going to have a pointer to the path that I have not yet taken yet, right? So PTR. And that's it, right? You can keep track of that pointer and you can come back and you can follow this pathway all the way down until you're done. And then you can pop this off of your data structure and then follow this T pointer. Great. So the traversal idea is that you keep track of the paths that you have not yet followed, right? Using a separate data structure that keeps a pointer to the path that you need to explore. And in our case, it's going to keep some additional pieces of information. So how do we go from here, which is we have our prefix try, we know how to do tree traversals, visiting multiple nodes. We know how to do perfect match. How do we go from here all the way to fuzzy matching? Well, let's say that the thing that we're looking for, our subject, is going to be ACT AA, right? So hopefully you guys see what I'm trying to set up over here. I'm not going to find ACTAA because ACTAA is not in any of the fragments that I've stored in my prefix trie. And in fact, you can easily see that if only you replace this G with an A, this is going to be one mismatch, fuzzy match that we should be able to find. Okay, great. So let's talk about how the algorithm is going to go. So in the perfect match, our choices were 1, if path exists, 2, if path does not exist. Okay, and then we had some stopping condition, which is if you reached the leaf node. So this is the perfect match algorithm, right? You use the characters ACTAA. If path exists, so it's going to exist for the first character, you can get to this A. It's going to exist for the second character, you're going to get to the C. It's going to exist for the third character, you're going to get to this T. But it's not going to exist for the fourth character, which is A, because you cannot go from T to an A, right? Because the only children that this node here has is G and T. Okay, great. Let me, for the sake of, because we're going to need this, let's go ahead and number these nodes, right? Let's say that this is node 1, 2, 3, let's say 4, 5, 6, 7, 8, 9, 10, let's say 11, 12, 13. The order that I number these really does not matter. The only thing that matters is I want to be able to refer to them without actually drawing an actual pointer. Okay, so how we're going to modify the algorithm for the perfect match to deal with the fuzzy substitutions? Well, I want to be able to get to this step over here, ACT, so this step right here, realize that I can go no further and explore what would be the possibilities if my next character, instead of just quitting, was a mismatch, substitution, in this case, to a G or a T, right? So let's consider it, right? So if the valid path does not exist, the way that we're going to modify the algorithm is we're going to, let's say, add +1 to mismatch counter. And then we're going to explore the children with remaining characters that we have to search for, right? So here we're going to say traverse children. Okay. Fantastic. Okay. Then let's say for the path exists, right? If the path exists, we move on to the next character in our subject that we're looking for. and do not update the penalty score, right? So do not update penalty mismatch counter, let's call it. And move on to the next character in the path. Use next character in path. Great. So is this sufficient? Well, almost. Let's see if this is going to allow us to find let's say we limit the number of mismatches that we're tolerating to just one, right? So we're gonna go to ACT. We're not gonna be able to follow the path to the next A. So we're going to say, hey, I'm gonna assume that I had A to a G error, and I'm gonna explore all of the children of this 7th node G, right? And then I'm also going to assume that what if I had A to a T error, and I'm going to explore all of the nodes below, right? That's the idea. Okay. That's good. One thing I want you to note is, what about this path? A, C, A, A, right? A, C, A is one of the queries that we added to our prefix try. It matches, A matches here, C matches here. We have a mismatch here. A matches, A matches. This is a valid one mismatch away potential answer to your fuzzy matching, but you would not be able to get to this valid answer using this particular algorithm, right? And the reason you won't be able to do it is because if at C step, AC, actually at T step, there is a valid path, right? So you're never going to follow down this branch if you could have gone past into this branch, right? So we're going to adapt our algorithm a little bit. And we're going to say, if the path exists, we are going to not update the mismatch and use the next character in the path like we did for the perfect matches, but we're going to add one more condition. So we're going to say add +1 to mismatch counter. And explore and traverse all the children. Okay. Okay. So that's essentially it. That's the gist of the algorithm, right? If you can follow along like you're supposed to with the prefix try, do so. If you cannot, add 1 to the penalty score and then explore all the children. And don't forget this special case where what happens if there is a mismatch that you want to introduce now, then hopefully catch some suffix that is that could have matched your original prefix. Okay, so I actually have put together a PowerPoint presentation. So let's go through and do this exercise in the PowerPoint presentation. So what you see over here is the tree, very similar to the tree that we've created already. There we go. ACT, GT, all of the 6 fragments that we've had. I have the dollar signs, which are not strictly needed, but that's okay. So let's go ahead and try this exercise, right? I'm looking for ACTAA. I'm going to follow the characters of the thing that I'm searching for, and I'm going to use that to follow the path through the prefix trie. So I'm in the root, node number 0, so right here. Do I have a node hanging off of it? Yes, I do, right? Great. So I move on. So which of the options am I in? I'm in the path is available. Can I add maximum? Can I add one to the mismatch penalty and then explore the children? Well, not really, because there's only one child. Okay, great. So now I'm in this node over here. Now let's go ahead and put it onto the stack just for the sake of argument. So the sequence that I'm trying to explore is ACTAA. I'm currently at 0, node number 0, which is my root, and I have 0 mismatches. Okay, great. Move on to the next element, which would be BTAA. I still have 0 mismatches. I've used that first A character, and I'm now in node number 1. Great. I only have one child, and that is a C. So that's the only step that I can make. Great. So I pop the element off of the stack, and I put the child onto the stack. So that would be TAA is what I have left to go. I have 0 mismatches. I've used AC as the path to get me here, and I'm currently in node number 2. So this node over here. Okay. Want to make sure that everything is visible. Okay, great. So this is the first scenario where I have 2 possible paths to go. I can go down this path, or I can go down this path. Great. So let's go ahead and do that. How do I actually go down both of these paths? Well, I put both of these options into my stack, right? So my stack then is going to be ACT is how I got here. AA is what I have left to go. I still have 0 mismatches, and I'm now in node number 3. Great. So that's one option that I got to explore. This is this path over here. Now to explore this path over here, I'm going to say ACA is how I got here. AA is what I have left to do. I now have 1 mismatch, right? Because I had to change that T to an A, and I'm going to be in node number 4. Great. So this is the first time when our stack, our to-do list, has more than one element. So we're going to pop one element off. Let's say this one over here. I'm going to keep track of it over here. You'll obviously be keeping track of it as variables. So I'm currently considering AA 0 mismatches ACT on position 3. So this path over here. So I'm now in this node 3. Great. I have two options here, right? I can go down the G path, or I can go down the T path. Let's go ahead and add both of those to my stack, right? So going down the G path would take us to ACTG. It would cause us to introduce one mismatch, right? Because we wanted to go to an A and there's no A. I have only A left to go, and I'm going to be in node number 7 if I was to follow that path. If I was to follow the path to the T, this path over here, again, I have A left to do. I have one mismatch, the A to a T. ACTT is how I got there, and I'm going to be in node number 12. Great. Cool. So I'm done with all of my possibilities, right? So great. I'm going to need to pop the next element off the stack. Let's go ahead and instead of deleting it, let's go ahead and just cross it out so we remember. Now I'm looking at AA 1, ACA 4. So I'm in this node over here, right? There's only one path that's available to me. Let's go down to the A branch. So we're going to go ahead and do that. I have left from me A. I am still at 1 mismatches, right? Because going A is the next character that I had to go to. And the way that I got there was A, C, A, and A. And I'm going to be in node number 5. Okay. Just for the sake of argument, I'm going to go, let's delete this. The next element I'm going to pop off of my stack is going to be this node number 7. So now I'm in node number 7. Let's delete these so that they don't confuse us. I'm in node number 7. I'm over here. I only got one character in my path left to consider. That's an A. There is no A path. Oh no, there is an A path, right? I can go down here. So, and this would be the leaf node, right? So that means that one of my solutions is going to be empty, one mismatch, A, C, T, G, A, right? So this is a one mismatch possible way for me to, when I'm searching for ACTAA, to traverse through my tree. Great. We're done. Technically, I could follow each one of these paths, and you should add them to your stack. But at that point in the game, you're going to exceed one mismatch. And let's pretend for a second, we don't want to consider every single possibility. And as soon as you exceed one mismatch, for now, let's pretend that we give up. Okay, so the next element that we're going to pop off is this element 12. So we are now over here. There's one and only one path away from for me, and that actually gets me to the leaf node, so that's great. So the second way I can get to it is I have no more characters left to do. I have one mismatch, and the way that I got there was ACTT, ACTT, and an A. Great. So the only thing that I have left is to pop off this element over here. So I'm now in node number 5. So I can get there 0, 1 mismatch, and the way that I got there is AC A, right? So it's a little bit verbose, but hopefully everybody can see how we can get all the way through the fuzzy searching and find all possible, in this particular case, 1 mismatch away fragments. We don't have to set some sort of maximum threshold here, but it is going to have significant implications if we don't. Okay. So let's clear this. And get back to our notes. Okay, so what we have here is an algorithm that is a composite of a perfect match algorithm with a little bit of tree traversal. If you can't find a path, or even if you can, add the mismatch penalty and traverse through all of the children. Great. So what does this mean for our timing, right? Remember, in the perfect case, so search, in the perfect case scenario, perfect match, for our problem, where we had big N queries, all of them were little n, and our subject was O of G, it would have taken us O of G, because all of the little n fragments that we have to consider. And the depth of the tree was O of n, so the worst case scenario, you wouldn't exit early through the prefix search try process, and you'd have to go to all the way to the bottom of the tree. So in the perfect case scenario, this was the complexity of our search. In the fuzzy matching scenario, things are a little bit different, right? So essentially, on the very, very first node, we either follow the path, which is great, or we explore all of the children. That's a bit of a problem, right? Because we know that if we start traversing through the whole tree or the whole try, the time it's going to take us to do the traversal is O of n, that's how many fragments we had, times O of little n, which is how many characters we've had in our fragments. Right? So the worst case scenario for a fuzzy search is that we still have O of G different subsequences that we have to create out of the subject. And in an unconstrained fuzzy search, we would have to do a full-blown tree traversal every single time. Now, this should remind you of something, right? This is actually a Smith-Waterman complexity for the search. But we don't want to be in that situation, right? Because that's for our problem, that would take several hundred years. So in practice, what you do is you constrain the total number of mismatches that you're willing to tolerate, so that you don't have to go down all the way to the bottom when you're doing the prefix try search. You only have to go to 1 if you're tolerating, or 2 levels down if you're tolerating, let's say, 1 or 2 mismatches. So in reality, this is actually the worst case scenario. In practice, your fuzzy search with a prefix try is something like this, that is in between the perfect match and the Smith-Waterman implementation. And this middle term question mark depends on the number of tolerated mismatches. The more mismatches you tolerate, up to every single possible character, so little n, the more issues you're gonna have. Okay. All right. That is it. That is essentially the central idea between fuzzy searching in the prefix trie. Explore the different possibilities, assuming that you've made a mismatch on a particular location. Okay, with that, good luck and have a wonderful day.